In this video, we're going to take a look at feature-based modeling inside of Autodesk Inventor. Here inside of this model, feature-based model.ipt, from our working files directory, we're going to examine certain concepts which are key to the software. We're going to begin by looking on the left-hand side of this particular interface, and we can see that we have our model browser. That's what this guy over here is called. And we can see a certain list of items in this tree. We'll begin by taking a look at this origin folder by expanding it. Here we can see a standard Cartesian coordinate system designed with the XY, the XZ, and the YZ planes. We also have the X, Y, and Z axes and a absolute zero origin point. As we hover over top of them, they do highlight on the screen to let us know where they are. The use of origin planes is very crucial to any sort of intelligent design inside of 3D modeling software. These features do not change no matter what. They are very static, very stable features. You can always rely on your origin. I'm going to reduce that by hitting the minus there. And next, we can see we have a series of features, such as extrusion, face draft, fillet, shell, and others. The types of features that we see in this tree can be subjugated by two different categories. You basically have sketch-based features, such as this extrusion 1, which required a sketch to help create it. And there, as I hover on top of the sketch, you can see basically how that was a couple of rectangles perhaps put together with some dimensions on them. We also have another category, which is pick-and-place features. Those are items like the face draft and the fillet, which do not require a sketch to be generated in order to create the feature. Now, these features are not added to this tree in a random order. They are not added here alphabetically. They are added here as a timeline. So essentially, this part was initially created with this extrusion at the top, and then other features were added to it to build onto that feature throughout the design of the part. Now, to better understand how this particular part was built, we're going to do a nice little trick inside of Autodesk Inventor called rewinding the history. So if I go here to the end of part marker at the bottom of this tree, I can click and hold on it and drag it back in time higher up the history tree. And what will happen is where I drop it, let's say right here above face draft, it takes me back in time to when that feature was created and before anything else was created after it. So this is your little time machine. So you can drag this up and down through your history tree to examine how something was developed. So here I can see this initial sketch helped create this feature, extrusion 1. And then if I drag this below face draft, you can see a small draft was added to this part. And now I drag it below fillet 1. You can see the smooth edges were added to this. If you were doing those particular types of fillets in an archaic 2D drafting system, it'd be very tedious to do so. Here it's quite easy. And then we have a shell. Well, what did the shell do? I don't see anything. Well, it's because it's on the underside of the model. If I rotate this, you can see the bottom side very easily. Rotation in the software can be done in numerous different ways, just as a little tangent here. But if you're having trouble with the rotation right now, just go ahead and use this cube that's in the upper right. If you click on the home icon, this little picture of a house, that'll take you back to that standard isometric view. Next, we'll go below to extrusion 2. Again, you can't see anything happen because it's actually on the underside. Here, a protrusion was added to this. And then we'll go down to extrusion 3. You can see a hole was added to this, a slotted hole. And then another fillet to smooth those edges there. And then we have hole 1. And then a mirror operation to mirror that across our origin plane. If I expand the plus sign there and the features underneath that, you can see how that took that hole and included it in that mirror. I'm going to redact these items. So this is a look so far at feature-based modeling. Now the next thing we want to take a look at is how these things can help us change. What happens if we destroy something in our history of this feature-based model? So if I come back up here to the shell, this shell created this wall thickness all the way around the part. After that, an extrusion was created on the inside of that wall thickness. If I were to right-click on the shell and choose delete, what do you think will happen? That's right, you're going to lose that extrusion. It'll become sick or damaged. So let me choose delete here. And again, a dialog box that says, Would you like to delete the dependent sketches and features? I actually have an option to keep them here. However, it's not going to do me much good based on how these were developed. So here I'll allow that to be deleted and choose OK. You can see I lost a lot of my history simply by deleting the shell. Now, if I'd like to undo that, I'll go up here to my quick access toolbar at the very top of the screen, and we have our undo command. I'll choose that, and I get my features back. Now, what if I deleted the shell and chose to keep those features? Here, I'll choose OK. And essentially, I kept the features, but they are sick. That's what this little icon in front of it means. It also lost my references for how that extrusion needs to be created. So instead, it created a few work features, these yellow features here, to help me still be able to create that. But there's really not a lot going on except for that slotted hole through the center. So let me rotate this back, and I'm going to undo to get my shell returned to me. This mirror operation that we did with the hole is also pretty neat because it updates based on how the original first hole changes. If I were to double click on hole 1, it takes me in to modify the hole, and I can modify the dimensions for which it's placed. So right here is an 80 millimeter. I'll change this to 100 millimeter. I'll hit my return key, and it updates that hole placement and also the hole on the other side, because this hole is a child of this parent over here. So we have parent-child relationships that are in play. Much like the shell was a parent to this extrusion feature, so is the mirrored hole to this one over here. We have our parent-child relationship. Now, for parametrics and feature-based modeling to work correctly, you do need to make sure you define things fully. If I take a look at extrusion 2, if I expand that down, I can see sketch 2 in there. If I were to double-click on sketch 2, you can see I have some dimensions on here that define its shape. However, I have not defined its location. It is still a very loose piece of geometry. If you don't lock this down, your model could update in an unexpected manner. For instance, let's say the slot is out here, but somehow I go back in my history and I make the overall width of this part a little bit shorter. Then what's going to happen is this extruded portion here, as well as the hole that follows it, is going to be hanging out somewhere in space out here, which is obviously something we don't want. So we need to define this with a dimension. Go up here to the top and choose dimension, and just choose to put a simple value in here of 40 from the center point to this line. Now this line is a projected reference. This is basically saying that when this edge updates, so does this location of 40 here. Also very important to our feature-based model. I'll right-click and choose OK to finish my dimension command, and then right-click again and choose Finish Two-Dimensional Sketch. So I have a little bit better location on how that extrusion is located. In this video, we're going to take a closer look at parametric features inside of Autodesk Inventor. Here with the Parametric Features IPT from our Working Files directory, we're going to examine this a little bit deeper. We're going to play with this particular part a little bit and just experience how we can make changes to a model effectively. Let's begin by examining the history. On the left-hand side, I can see there is a simple extrusion here with a sketch that helped create it. So that's our sketch-based feature. And then we have a fillet. So two simple features to interpret what's going on with this design. Let's begin by examining the first sketch here. I'm going to double click on it to activate it. And we can see that we have a series of lines, circles, and arcs, as well as dimensions that helped shape this particular sketch. There's also an anchoring point here on the circle on the left-hand side. This is actually anchored to our origin of the file. If I expand the origin folder, I can see the center point is tied right there. If I look at the axes, you can see they're also referenced there as well. Since this is tied to the origin, this center point will not move. If I make changes to this, such as the overall length of 2.5, it should stretch to the right. So let's double click on this, 2.5 inches, and here I'll change it to 3. I'll approve that check mark. So you can see based on that anchor point of the origin, it updates in an expected manner and makes it grow to the right. Now, if I make changes to anything else in here, such as this diameter, I'll go ahead and double click on that and make it 0.375. I'll approve that check mark there. You can see it changes not only that circle, but the circle down on the right-hand side. That's because they have a relationship between them that when one updates, so does the other. Here I'll change this back to 5 by double-clicking on it and have it be that 0.5 value. I'm done looking at this now, so I'll right-click and choose Finish 2D Sketch. And that returns us back to our part modeling environment. And you can see that the part actually got a little bit longer because that sketch that helped define that feature also got longer. If I were to double click on the extrusion 2 here, basically you'll be able to see how that was given thickness. So here this is currently 0.15 inches tall, and that's going in the positive Z direction. How can I tell it's a positive Z direction? Well, I can look at this triad in the lower left down here, and I can see the X, Y, and Z Cartesian directions in space. Now I can change these values here, such as currently 0.15 inch to 0.25 inch. You can see a dynamic update happen as you do that, and I'll prove that with the green check mark. Now there's other ways you can change the model dimensions without having to go into the sketch or going into the feature. If you were to right-click on your extrusion and choose the option called Show Dimensions, it will give you the dimensions for the sketch as well as the dimensions for the feature. So here you can see the 0.5 value I changed, the 3 value I had changed previously, and also the 0.25, which is my overall height of this design. So here I'll change the 3 to a value of 3.5. I'll hit Enter to approve that. I'll change this to 0.375. Check mark that to approve it. And for my thickness value, I'll change it from 0.25 to 0.125. Now, before I approve this, I want to point out the fact that this dimension is called D23. As you're applying any sort of value to your model, whether it's a sketch dimension or a feature value, it's creating these D placeholders. So let's remember D23 for a moment. Let's go ahead and approve that. Nothing happened here. Nothing really updated with the feature model. You can see the underlying sketch updated, but the overall geometry has not. Whenever you use the Show Dimensions method of design, you have to force the update to actually take place. So if I go up here to my Quick Access toolbar, there is a lightning bolt icon. If I click on it, it will force the update of the model so I can see everything change. If you were to use the sketch editing or the feature editing directly, that doesn't happen. You can basically update it automatically when you finish the command. Next, let's take a look at the fillet. If I were to double click on the fillet, I can see that it has a radius value currently of 0.03125 inches. Now what happens with this value is it stays independent of any other feature that's currently being built. So if I made my thickness of this so small that it invalidated my radius, I would have a problem. Let's try that. So currently I have a thickness value that is okay for this particular radius. But let's say I try to change the radius to 0.125. Now, as you're seeing, the preview here doesn't look too good. If I approve this, I basically have a fillet that kind of shaved off the top half of my design. It didn't really give me a fillet on the top side, but a very large one on the bottom. I'm going to go back and double click on fillet again. And let's say I change it to 0.188. I'll approve that again. And again, it still is creating a very inappropriate sort of fillet for this type of design. I'll go back to fillet again. And instead of trying to just put any old value in that would work under one circumstance, maybe I'll put a value in that would work under all circumstances. I'm going to create a parametric relationship between this fillet radius and the thickness of this plastic piece. Do you remember D23? That was the value of my thickness value for this part. So I'm going to have it equal to D23 divided by 4. So no matter what happens to D23, this radius value will always be that divided by 4. A very simple equation to get your design intent across. Just to check how that works, let's go back and use a Show Dimensions on our extrusion by right-clicking on it. And here, we'll change this from 0.125 to 0.5, much thicker. I'll go ahead and update this. And you can see the fillets maintain a size that is the relationship to that overall thickness value. I can't stress how creating good relationships inside of an Inventor model is key to working effectively in this type of software. If you have designs that change in an expected manner, everything is going to update more effectively, and you'll have less problems trying to repair geometry that was not created in an effective manner. In this video, we're going to take a look at the idea of associative files inside of Autodesk Inventor. Here I have 4 files open from our working files directory: long slot runner IPT, loader IAM, loader IPN, and long slot runner.dwg. An important concept to understand about 3D modeling software is that changes made in one file can definitely affect changes into other files. So here the long slot runner IPT is our core modeling file. This is where all of our design intelligence takes place, our sketches, our features to help design and shape individual parts. Once this part has been finalized, we can actually put it into a IAM, or a Inventor assembly. So I'm going to go down here to the bottom and click on Loader IAM. And here you can see the entire loader, and it has this long slot runner piece on this side of the bucket, as well as the other side. Now, this assembly, once completed, can be utilized to create an exploded view, which is our IPN. So I'll click on that one down there. This is an explosion to show disassembly or just an exploded view to get a better idea of how to document it for balloons inside of a drawing. Again, the long slot runner piece also exists here, as well as the IAM in general. In our last file, the long slot runner DWG, if I click on that, is a documentation piece of the long slot runner showing the different sizes of the hole locations and basically general documentation about that part. Now, it's an important concept to understand that the long slot runner IPT that's been utilized in these other files is not copied into those files. It is not a unique instance of the long slot runner as it gets put into those files. It is essentially a hyperlinked file, so that as the long slot runner IPT updates, so does the loader IAM, the loader IPN, and this drawing file. So let's take a look at that interaction. If I go back to the long slot runner IPT, I'm going to make a change to this. I'm going to use my Show Dimensions command by right-clicking on Extrusion 2 and using Show Dimensions. I'll change this from 5 to 6 and approve that check mark. I'll go ahead and update this file so you can see the length change. I'm also going to come in here and use my Show Dimensions again. I'll change this from 0.5 to 0.625 and also update that. So you can see there's changes that have taken place inside of this one IPT. When I go to the loader IAM, there is a pending update taking place. If I go to the very top and click on Update, you can see it updates with the longer version of that file, also the larger holes. If I go to the IPN file, that automatically updates. There is no update inside of this file. There's just an automatic link to the assembly. And then on the drawing file, again, you can see it automatically updated and the dimensions are hooked onto the geometry correctly, so they automatically update it as well. Let's go back to the long slot runner and talk about this a little bit more. Let's consider that this IPT was utilized in 50 different designs. So I can basically make a change to 50 different assemblies, to IPN files that might be created and other documentation pieces all at once by changing the one IPT. That's why file management inside of 3D modeling is very crucial to effectively working with this type of system. Understanding your relationships and your associative files and how things are linked together can become a very effective way to create your designs for market. Conversely, if I didn't have this sort of functionality, if I had to update 50 separate drawing files, 50 separate presentation files, it would take a very long time to do so, and I would have a lot longer time in design and overhead before I ever got my product finished or any updates to those products. In this video, we're going to take a look at assembly and management techniques inside of Autodesk Inventor. Here I have a loader assemb manage IAM from our working files directory. And this is a completed design that has all of my IPTs put together. They've been assembled using assembly constraints, which basically hold our parts together. So we can define how these things will come together in the overall arrangement by use of geometric rules and conditions we apply to our model. And what that allows me to do is come in here and pull on something such as this wheel and have it spin without having it come loose of the axle. Now, our geometric relationships we have in here all get stored in a folder at the top left here inside of an assembly. You can see all these different types of relationships I have, a lot of insert relationships, angle relationships, things of that nature. Here, I'll just redact that. And we'll also take a look at how to look for issues where we might have overlapping parts, such as an interference. If this was a two-dimensional CAD system, the process of looking for interferences or things that overlap each other is a very tedious process, and you have to stare at a lot of different lines to figure out if something is actually indeed overlapping. Here inside of Autodesk Inventor, it's a lot easier. So we can go up to our Inspect tab, and we can click on this command called Analyze Interference, and we can define our set by clicking on them or creating a window around the parts we want to analyze. Here I'll choose OK, and it's going to tell me I have these different interferences going on. Now, some interferences are good, some interferences are bad. If we have an interference of a press-fit dowel or a screw thread interaction, that's okay, we expect that. However, if we have an interference where two blocks are blatantly overlapping each other, that can be a serious problem. So here, if I were to zoom in, you can see I have some threaded engagements going on. I have some rings right here. This is actually from a rubber piece that's getting compressed, so I'm okay with that sort of interference going on there. Now, if I come down here, I have a little bit of interference with this plastic nut screw going into the tire. So maybe this needs to be backed up a little bit. That's a small interference. I probably don't care too much about it, but at least I know that it exists. If I had blocks overlapping each other, it would definitely stand out, and I would have to go in here and change how things are put together. Let me choose OK to close that. And these interferences don't stick around forever. When you start to scroll your mouse wheel after exiting the command, they do go away. Now, something else to look at in here is range of motion. So let's say this bucket here, I don't want to have it always raised at 45 degrees. I would like to have it come down a little bit or actually go up higher perhaps. I just want to check that range of motion to make sure it makes sense. Now you can probably look at this model and say it's going to be okay, but let's just take an example here. If I scroll down to the long slot runner 1, I have an angle of negative 45 degrees, maintaining a geometric hold to keep that bucket raised at 45 degrees. So if I come in here and try to pull on this, it's not going to come down. It's being held there. If I change this angle value from negative 45 to 0 by simply changing it in the bottom there when it's selected and hitting enter, it's going to update that geometric relationship to have that drop the bucket down. Now I can also have that be negative 90, and that's going to go straight up, or return it back to the 0 value. Now if I want to see a visual change of that motion, what I can do is right click on the angle 9 here and choose the option called drive. This will take my constraint and drive it from one value to another. So I'm going to start here at a 0 value and end at negative 90. And basically just play this in reverse direction because I'm going in the negative direction or the positive direction, depending on which way you're going. And you can see that range of motion taking place. I can record this out to a video, put this into a PowerPoint, put it on a website, take it to a meeting, do lots of different things to allow me to show the range of motion to different third parties. Here I'll choose cancel it to get out of there. And the next thing to take a look at is how we can export all of our data about this file. When you build a design, you might have procurement systems, you might have people that need to do purchasing on this, you might have to export a bill of material for sales or for the shop floor, or just a general bill of sale. So what I'm going to do next is take a look at our bill of material command, which is on our Assemble tab, and I'll choose the bill of material command from the Manage panel, and this will open up a window that shows me all the different types of elements that make up this design. So here we have our Model Data tab, and this shows me the part number, a thumbnail for it, the bill of material structure, unit quantity, stock number, and description and revision. I can also include or exclude different columns to have different types of data reporting into my bill of material. Now, I also have some different tabs in here, so we'll spend a whole video session talking about bill of material, but one of the most important things to understand about this is you can export your bill of material here to different text files, Excel files, Access database files, whatever you might need to get this out of Inventor and into a different software package for those reasons I mentioned. Now you can also make changes to your data here as well. So for instance, if I think this stock number needs to be something different, you can see it highlights. And I say, well, you know what? The stock number is actually something else. Or if I want to fill out the description here, I can do that. And it will save that information back down to this original file. So I don't have to go back to the file explicitly and do it. I can do it all right here through assembly management. I'll go ahead and close this bill of material command. And this has been a look at some of the assembly management tools we have inside of Autodesk Inventor to better understand what we're going to have available to us. In this video, we're going to learn how to create model documentation and understand the concepts around that inside of Autodesk Inventor. So here I have a circle plate IPT and a circle plate DWG from our working files directory. Inside of this IPT file, I can see I have a fully defined model with my extrusion and my fillet. It has all the holes in it, it's sized correctly, but I can't necessarily give this to my shop floor and say, hey, go ahead and make this. I would like to have a 2D documented print to accompany anything I might send off to the shop floor. Yes, you could open up a viewer on the shop floor if you're a progressive company that likes to do electronic documentation. However, a lot of shops still want to have a two-dimensional print. You have to have that for catalogs, for sending out to clients, for quoting, things of that nature. So we need to document this somehow. I'll go over to our circle plate DWG by clicking on that at the bottom of the screen. And I need to place in views of that model and then put dimensions on them so someone can better understand what this design is really about. Now, as mentioned in other videos, this is basically not copying in the file, it's simply referencing it in. So if I were to give this DWG file to somebody without the IPT file to go along with it, they would not be able to open it up effectively and work on it. These files are associative and they work together. In order to start placing in views, I'm just going to right click and choose the base view command. The file that's currently open in memory will appear, and I can simply place this where I want. I can even choose a different orientation to look at, but that's fine for me. I'm going to click over here as well, and also to the upper right. So I'm basically creating orthographic and isometric views of this design. When I'm finished placing my views, because I only really need the two views there in the front and the right, I'm going to right click and choose OK. Now, if I need to modify these views for scale, I can do that. If I need to change the shading or showing of hidden lines, I can also do that. As an example, I'll just double click on the one in the upper right, and I will toggle this one to a shaded view by choosing that button and hitting OK. So I got the overall look to start documenting this. I got enough white space around my views to put dimensions in, so let's go ahead and do that. I'm going to right click and choose General Dimension and simply place on a dimension here for that circle. I get a box that pops up if I want to make any additional changes to that particular dimension. I don't. I'm just going to choose OK. And come over here and put a dimension between these two lines to show my thickness of that. Again, I don't need to add anything else here, so I'll just have the value. Now, you can also add in things like center marks and center lines. If I go up here to my Annotate tab, I can go here to my symbols, and I can actually start placing in center marks or centered pattern references. So you pick your original center first, and then the items you want to place on a centered pattern around that. Right-click and choose Create. Cancel out of that command, and then choose General Dimension. Then here I can document that bolt circle. Here I'll put BC behind it for bolt circle. So you have a better understanding of how this is being documented now for size and shape. Now, if I make a change to the IPT file, let me just cancel out of this command. Go back over to the circle plate IPT. We'll come in here and make a few adjustments. I'll go ahead and double click on sketch 1. And here I'm going to make the size of the circle 0.375. I'm going to adjust the bolt circle here to move up a little bit. Instead of 1.25, we'll do 1.375. And I'll change the circle in the center as well to be 0.625. So you can see there's quite a few changes taking place there. I'll finish our 2D sketch by right-clicking and choosing that option. I'll double-click on our extrusion 1 here. I'm going to make the thickness a little bit bigger. I'm going to make it 0.375 for the thickness of this plastic. Okay, that. I'll double-click on the fillet and change this from 0.03125 to 0.125. Now let's jump back over to the circle plate DWG, and we're going to see those changes automatically take place, as well as the dimensions will also automatically update. So our model documentation is kept updated based on our IPT. We can see why if we were missing the IPT file, then we would not be able to have these updates take place. This is referenced in. It is not copied in.